Okay, look at examples E, F, and G. They look very similar to each other, right? They have different names, f of x or f, g, and r, but the numerators are both the same, or all three the same. The only difference is the denominators, which are all quadratic trinomials, they kind of have slightly different configurations, okay, or different numbers. So I'm going to try and work these three kind of as a group because the purpose to have all these three is to compare and contrast, all right? So if I were to start either one of these or any one of these three, my first plan of attack would be to notice that there is a square root with a variable underneath it, right? See that? So we would come off to the side here and say 5x minus 3 is greater than or equal to 0. And I'll show you where the points would come. Like if this were the quiz question tomorrow, you'll have one quiz question tomorrow, and it won't take the whole period. In Algebra 2, I know the quizzes took all period. It'll be a quick one question quiz like this, and I'll give you like 10 minutes to do it. And then there will be like 8 or 9 checks that I'm looking for along the way. So even though it's one question, it's not like you get it right, you make 100, you get it wrong, you get a 0. I'll divide it up into several things. So like this one right here, this might be worth like 8 points. One check, setting the whole thing greater than or equal to 0. Now this is a linear inequality, so we can solve it algebraically. We just got to remember possibly to flip the inequality if we multiply or divide by a negative. But in this case, I just add 3 to both sides, and I divide through by a positive 5. So I get x is greater than or equal to 3/5. You'll get another check for coming up with the value of 3/5. The inequality will come later. Now we just quickly double check, right? What is the number bigger than 3/5 that we claim works? 1, right? 5 times 1 is 5. 5 minus 3 is positive. Who cares, right? It's 2, but it's positive. Who cares? It's positive. That's what we want. So I got that part done. Now I look at the denominator, which is x squared plus 2x minus 3, and I say the whole thing can't be 0. And that is going to be your third check in this case. The second thing we look for, a variable in the denominator, the whole thing can't be 0. And then we factor it. It looks like it's factorable. So this looks like it's going to be x plus 3, x minus 1. I'll get it. And once you factor it, I do, yeah. Hello. Oh, yeah, she said, yeah, that you can come sit in here because you're going to transfer. Yeah, you're going to be in here full time eventually, right? Yeah. All right. So it looks like we got 2 front row seats. Let me make sure these 2 are still open and it's not someone that's absent. Yeah, that one's open if you want. That one's open if you want. Either one of them. If you forget to bring down the not equals 0 at this point, you're going to lose that third check that you just earned on the line before. So make sure that those details you're starting to pay attention to. It's still an equation or a non-equation. Now, instead of setting them both equal to 0, I encourage you to remember to use the factor theorem that says if x plus 3 is the factor, the corresponding root, or 0 as we call it, is negative 3. And if x minus 1 is a factor, the corresponding root is positive 1. If you're listing, like, no, not if there's enough space in between them. Yeah. Obviously, right, if you don't put the comma between them and you just put negative 3, 1, that looks like negative 31. But if, yeah, you don't need the comma between them if they're spaced far enough apart. All right, so you would get a check for this value, and you would get a check for this value. Oh, yeah, slash, sorry. Yeah, not equal to. Do you know what we're working on? No, okay. Go to the internet and go to corpisworld.com. Korpi. K, the K? No, K. Your fingers in the wrong place. K-O. Here, yeah. Let me type it in. Korpisworld. Corpus World. There we go. Click on that. Click on pre-cal. And then we're right here, 2.1. Algebraic domains. There's your notes. You can upload those into Canvas now. Okay. All right, so now we have to put the 2 together. We only want to exclude the values that give us division by 0 if they happen to fall in the interval. So are either of those 2 values bigger than 3/5? Yeah, the 1 is, right? The negative 3 is already excluded by the inequality. We don't need to worry about excluding it again. So here would be our final answer. It would be d sub f is the set of all x such that, and in set builder notation, it's just easy. X is greater than or equal to 3/5, comma, you do need the comma there, x can't be 1. So what you would get here is you now get credit for the inequality in the right direction, and you would get credit for excluding that value only, and then you would get an 8th check for the notation here at the end. If you were to also say x can equal negative 3, you would lose the 7th check because you don't need to state that again. This is a popular class this morning. Hello.
Alright. Oh, I think I got my schedule changed.
You're in here now?
Yeah.
Okay. Let's just sit you in here and we'll check out the details later. There's a desk open over there, and there's 2 in the front. Front row are kind of high dollar seats.
Okay.
I don't know. Can you afford those?
I don't think so.
All right. Now you can also do it in interval notation. Get out your iPad and go to a browser, and go to this website right here. Go to I'll have to write right here. Go to Corpy's World, KORPISWORLD.com, and I'll show you where you can get these notes from that website. All right, so now in interval notation, I'll say or it's d sub f colon x epsilon. That's part of the notation, and then we would say bracket 3/5 up to 1 with a parenthesis, a union symbol, which means or, another parenthesis with a 1, and then we cruise to infinity. And remember, infinity and negative infinity always get parentheses. So that's how you step over a taboo value. You go right up to it with the parenthesis, union, pick back up with the parenthesis, and keep going. All right, good. So now we're going to click on precap. And everything's going to be in Canvas eventually, but we're on 2.1 algebraic domains on those notes. So you can upload those into Notability. Here, and can I also have you, you're in this spot here. Go ahead and sign your name right here, or just write your first and last name. Okay, good. And then if you can, you are right here. Go ahead and write your name in that spot, first and last. All right, so that one would be worth eight checks, and each check might be worth only like 8 points. So no quiz is ever worth 100 points. Like if we have 10 checks, you might think each check would be 10 points apiece. They wouldn't be. They would be probably 8 points apiece. So that's kind of like a 20-point curve, right? You miss them all and make it 20. In this case, if there were 8 checks, they might be 8 points apiece, which means there's a 36-point curve. Miss them all and make a 36, right? That's a pretty good deal. It's not the best way to become valedictorian of your class, but if you want free 36 points, just miss them all. Wouldn't recommend that. So that would be designed to take you 10 minutes, and then you would need your own paper. You would take it in 10 minutes. You would take a pen out. So you'll need a pen. Put your pencil away. Take out a pen, and then we'll go over it just like we did here, and you'll award yourself points, and then you'll score it yourself. Put the grade at the top and pass it in. It's already graded, and you already know what you did correctly, and you also know where your mistakes were so that you could fix them. It's immediate feedback. So that's how we'll do all of our quizzes. 10 minutes at the most, plus maybe 5 minutes to grade. All right, any questions on E? All right, so if I were to then go to F, my first step would be the same thing that I did here. And I would come up with x is greater than or equal to 3/5. So I'm not going to do all the work again, but I'll just remember that. I'll put it right here. The demand of the radicand is that x has to be bigger than 3/5. But I have a different denominator now. So we have to do the same thing. X squared plus 4x plus 3. That can't be 0. Can't divide by 0. It's a quadratic trinomial equal to 0. So we F it. We factor it. Make sure it's not equal to 0. So that looks like it's an x plus 3 and an x plus 1. And now directly from the factors, you can pull off the roots of the zeros. X cannot equal negative 3. X cannot equal negative 1. There, I did it. I wrote them far enough apart so I didn't need the comma. But now again, we only need to exclude them in our final answer if they happen to be bigger than 3/5. Are either one of those bigger than 3/5? No. So they are already excluded by the demands of the radicand. We don't need to exclude them again, right? It's a non-issue essentially. So our final answer here would be the domain is the set of all x such that x is simply greater than 3/5. And if you had then said that x can't be -3 or -1, you would lose a point because it's unnecessary. You don't need to say that. A superfluous comment. Of course, in interval notation, I don't care tomorrow if you write your answer in interval or set. I probably won't make you even do both because just pick one. X epsilon 3/5 to infinity. We wouldn't need to step over anything. All right. And then letter G, which is R of x, same thing in the numerator. We have a radicand. Its radical is 5x minus 3. We set up our inequality, and we're back to the same demand of the radicand that x has to be bigger than or equal to 3/5. But we have a new denominator, so let's do that work. X squared minus 4x plus 3 shall not be 0. Bless you. And now we can factor it. X looks like x minus 3. X minus 1 can't be 0. Pulling the roots directly off of there, we get x can't be 3 and x can't be 1. All right. So again, only need to exclude them in our final answer if they're bigger than 3/5. And both of these, of course, being positive numbers, bigger than 3/5, we need to step over both of them. We need to exclude both of them. So we'll say the domain of R now, the function R, is a set of all x such that x is greater than or equal to 3/5, comma, you do need the commas here. And now you can just say x cannot equal 3, comma 1. If you don't want to put x equals again, you could just put 3, comma 1. Or 1, comma 3. In set notation, the order doesn't matter. It doesn't matter if we say it can't equal 3 or 1 or 1 or 3. It's just a list. And then we close the set with the brace. Or, if you're really into interval notation, it's x epsilon. We're still starting with 3/5 as a lower bound with a beefy bracket. But now we have two values to step over. And now the order does matter. I can't go from 3/5 to 3 and step over 3 because 1 comes first on the number line. So interval notation is always least to greatest. So we go all the way to 1, step over 1. We cruise to 3, step over 3. And once we get past 3, it's smooth sailing forevermore towards infinity. So there's the interval notation. The more excluded values, single excluded values you have, the longer your interval notation becomes because you're stringing together a bunch of what we call disjoint intervals, non-overlapping intervals. All right, and that takes care of example 5. Your quiz tomorrow will be, or Monday I should say, is one question like any of those, where you're going to have the possibility of dividing by 0 and taking the square root of a negative in the exact same problem. Two separate things, combine your results, state your answer. Should be pretty straightforward. Hopefully everyone will make 100. At least everyone will make a 36. Yeah, you're welcome. Questions on example 5? All right, let me quickly, since we had some attendance issues, let me quickly just post my attendance. If you want to look at example 6 and start kind of thinking about it, it's the exact same instructions. Find the domain, state it in set or interval notation. See if you could do A on your own. Think about A on your own. In fact, yeah, go ahead and do that. We want to clear those two hurdles and those two hurdles only, right? Are we ever dividing by 0? Are we ever taking the square root of a negative? Right now, if we clear those two hurdles, life is good. Domain would be all real numbers. Otherwise, we have restrictions. All right, Tuong, is that how you say your name? Tuong?
Yeah.
You're already on my roster, so that's good. Yeah, that's good. Yeah. Nathan, you are not on my roster yet, but that's going to happen, right? Okay. Okay, good. All right, let's take a look at this one here. We got three terms just to kind of review some of the vocabulary. Terms are separated by plus or minus signs. Whenever you have multiple terms, it's kind of like having multiple problems in one, strung together with plus or minus signs. In each of the terms, we can't divide by zero and we can't take square roots of negatives. So, do you see a denominator anywhere with a variable in it? With a variable in it? Yeah, you could either say the whole entire thing is over 1, which 1 is never 0, it's trivial, or you can look at each terms and I see one denominator, right? But is 3 ever 0? No, it's a 3. So even though there is a denominator, there's no variable in it, and it's not a 0, so we clear that hurdle. We're never dividing by 0. Do we have any square roots or fourth roots or anything like that?
Yes.
Yes. Now look under the square root. What's under the square root? What's the radicand? Is it 3 or 3x? Yeah, you got to look very carefully, right? That radical stops right there before it goes over the x. And you got to be careful when you're writing things like this on your paper. If you extend that radical like halfway over the x, oops, and it's not supposed to be, I'm going to assume that you're trying to cover the x. So in this case, our radicand is 3. Is 3 ever negative? No, he has a bad attitude sometimes, right? 3 is kind of negative, but he's not a negative value, right? He's positive 3. So we cleared both hurdles. Guess what the domain is if there's no restrictions?
All real numbers.
All real numbers. So here's what we'll say. The domain of f is all real numbers. That's the easiest way to say it. You just put the double bar r. That's the representative letter for that set. Or if you're just an interval person, it would be x epsilon. We would go from negative infinity all the way to infinity from left to right with parentheses around it. That's another cool way to say all real numbers. Sometimes those infinity symbols can be fun to make. I told you my jokes, right? Did we start the jokes yesterday? Did I tell you the joke? What did 0 say to 8? Nice belt. That's what 0 said to 8, nice belt. What did 8 say to infinity, though? 8 said to infinity, dude, you sleep with your belt on? Yeah, I made that. This Scorpy? Oh, it's in. It should be in. Okay, thank you. Let me check. She said my attendance didn't go through. I got a confirmation here that it did. Bear with me here. All right, so go ahead and look at the next one here. Figure it out on your own while I check this attendance matter. Are we ever dividing by 0? Are we ever taking the square root or fourth root of a negative? It's all over 1. That's not dividing by 0. We have an x in the exponent now instead of as the base. We call these exponential functions. And we'll study those later on in the year. We'll look at the base e to the x as our parent function. But this is 4 to the x. So every integer value of x, the value quadruples, 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 quadruples. It doesn't appear that we have denominators, and it doesn't appear that we have square roots. However, if we come off to the side here, we know already that I can look at negative exponents. If x was negative 1, that would make it 4 to the negative first, which is 1 over 4 to the first. That gives me a denominator, doesn't it? But is that denominator 0? No, it's a 4, so that's good. What if x were 2? I would have 4 to the negative second. Now that's 1 over 4 squared, which is 1 over 16. I have a denominator, but is it 0? No. Is there any value of x that's going to flip that and give me a 0 in the denominator? Is any power of 4 ever 0? 4 to any number, is it ever 0? No. So even though we get denominators, a lot of them, They end up being just non-zero values, so that's fine. So we passed that test. Now, is it possible to even get radicals out of this? Well, let's see. If x were equal to 1/2, 4 to the 1/2 power would end up being the square root of 4. So we do get radicals, but underneath that radicand, or the radicand itself, is a 4 again. It's not going to be negative. And if you look at 4 to the 1/4, it's going to be the fourth root of 4, which is still going to be a non-zero number or non-negative number under the radical. So we do get denominators, we do get square roots, fourth roots, but there's no issue here. We're never going to get any violation. So again, if that's all we're looking for and we clear both hurdles, guess what the domain is? Our real numbers. Yeah, so D sub G is our real numbers. And if you want to write that in interval notation, go for it. All real numbers. So answer choice 6A was all real numbers. Answer to 6B was all real numbers. I wonder if answer to C is all real numbers. Let's see. H of t. So our independent variable is t now instead of x. The function's name is Hortense, or H for short. Do we have a denominator? Let's look at that first.
Yes.
Yeah, but is it 0?
No.
No, it's the constant, irrational constant, 2 square root of 3. So that's fine. Do we have radicals?
Yes.
I got a couple of radicals actually, right? In the bottom I have a square root, but its radicand is 3, which is not a negative number, so that's cool. In the top, more importantly in the top, I have a radical with a variable underneath it. That's the one that's more critical. But look at the root index. It's a 3. Remember, we cannot take square roots, fourth roots, sixth roots, eighth roots, or any even roots of a negative number. But what about cube roots, fifth roots, seventh roots, or odd roots of a negative number? Are those allowed?
Yes.
I think so. For instance, if I look at this, the cube root of -1, what number times itself 3 times is -1? -1, right? What about the cube root of -8? What number times itself 3 times is -8? -2. What about the cube root of -27? What number times itself 3 times is -27? -3, so on and so forth. In fact, the cube root of a negative number is just a negative number. The fifth root of a negative number is just a negative number. So here's the question. Is it okay to have negatives under odd roots?
Yes.
It is. We don't have to try to avoid the negatives anymore. Now, if that cube root of t minus 1 were in the bottom, now we'd be possibly dividing by 0. But it's in the numerator. So we cleared both hurdles. Guess what the domain is? Our real numbers. Yeah. Cube roots, fifth roots, odd roots, variables, they're fine. Unless they're in the denominator. Then we still can't have a 0 down there. All right. So any questions on example 6? We'll quiz twice next week, more than likely. Probably quiz again on Wednesday. And your quiz on Wednesday will be more like example 7. Sometimes we'll quiz twice a week. Next week will be one of those. Wednesday or Thursday. It'll be like example 7. Look at the instructions are. Find the domain of each of the following. State your answer in set or interval notation. I kind of recognize those instructions from pretty much all the previous ones. We're doing the same thing, but it's a new example, which means that we're shifting gears here a little bit. There's probably going to be something new that we have to recognize about these types of problems that are different from the ones we've already, shall I say, mastered. Do we have a denominator with a variable in it?
Yes.
Yeah, we got that whole thing with a variable. Do we have a radicand with a variable in it?
Yes.
Yes, we have a square root even. So now it's important that it's a square root, not a cube root. So we're at risk of doing both things again. Is it time to panic?
No.
No. The expectation of the class, remember, is to stay calm. Safely stay calm. So we'll stay calm. We'll just go ahead and do what we did on example 5 and what you'll do tomorrow or Monday on the quiz. We'll just treat it as 2 separate things. Find them independently, combine the results. Nothing to it. All right. I encourage you, as always, to start with the radicand because it defines the majority of your domain. X minus 2 is greater than or equal to 0. Yes, it is. That's a linear inequality. It's x to the first power. So we can solve it algebraically. This one's pretty easy. Just bring the 2 across, and you get x is greater than 2. I'm going to quickly check in my head. Something bigger than 2, like 100, right? 100 is bigger than 2. 100 should work. What's 100 minus 2? Positive. You say 98, I say who cares? It's positive, so it works. Good. Now, the next part. What part of the denominator do we say can't equal 0?
All of it.
All of it. Trick question. What part of the denominator can't be 0? All of it. Okay? So we're going to say the square root of x minus 2 plus 1 shall not be 0. The whole thing. Now notice this is a little bit different than the ones we had in example 5. Now in example 5, when we had the radical in the bottom, it was the entire denominator. So that we would not want to divide by 0. So we'd have to exclude 2. Because 2 minus 2 is 0, and the square root of 0 works. We can clear the radical, but it left us with the 0 in the bottom. We now have this little helper value outside the radical. So we have to see how that affects the problem. When you set up these types of inequalities here, you set up what's called a radical equation. It's got a radical in it. And the first step in solving a radical equation or non-equation, whatever you want to call it, is to isolate the radical. Get it by itself on one side. Currently, we don't have it by itself on one side. But it's easy to get it there. All I got to do is subtract 1 from both sides, and I get all of that cannot equal -1. Now I need to get rid of the square root. How do I unsquare root something? Square both sides. And I'm not going to show that. You could put that to the second power. You could put that to the second power. I don't even think you need to show that at this level. Just square it in your head. On the left side, when you square the radical, you get x minus 2. And what do you get on the right when you square -1? Positive 1. Yeah. -1 times oops. Hang on. It's time that I figure out the eraser once and for all. How do you make your eraser smaller? Does anyone know? I used to click on it and I was able to. The dots? Oh, there it is. Okay, that's right. My eraser. Okay, thank you. Yeah, it's a pretty easy fix. I got it now. I feel so embarrassed. It was so easy. 1. And now we add 2 to both sides and we get x can equal 3. Now, back in the days from example 5, you would say, I know I only need to exclude 3 if it happens to be bigger than 2. Is 3 bigger than 2? Yeah, so I would need to exclude it. But, this is a little bit different than the example 5 because we have the +1. So I'm going to teach you what you need to do every time when you do a radical equation. This step right here, when we squared both sides, it should raise a red flag. Just like when you're solving a linear inequality and you multiply or divide both sides by a negative, that raises a red flag. You're like, ooh, I have to flip the inequality symbol. If you're ever solving a radical equation and you square both sides, it turns out that you introduce the possibility of extra solutions that are erroneous. Extra solutions that are erroneous. Do you remember what those are called? Extra solutions that are erroneous. Yeah, extraneous solutions. I can explain to you why extraneous solutions might sneak in, but I don't know if it's going to help you understand or help you do it. Basically, you're taking a power of 1, like a linear function that has 1 x-intercept at max, and you're squaring it, turning it into a quadratic that now can have 2 x-intercepts. So you're not guaranteed to have an extraneous solution. The value that you get might actually cause a 0, but it could also be extraneous. So you need to get in the habit, when you square both sides and you get a value that says is a solution, you check it. Does it actually cause a 0 in the denominator? Let's see. Plug it in up here. What's 3 minus 2? 1. The square root of 1 is 1. And of course, 1 plus 1 is 0. 2. Oh, it's not 0. It's 2. Oops, we just said he caused a 0 in the denominator, but he's causing a 2 in the denominator. My bad, x equals 3. My bad. You actually can be in the domain. You do not cause a 0 like I was led to believe. I do not need to exclude you. You're good to go. Welcome to Club Math. Have a good night. Okay? Now you might recognize that it's going to be extraneous right up here on this last blue line. The positive, there's an implied plus sign out here. The positive square root of a value, can it ever be a negative number? Can you take the positive square root of something and ever get a negative number? No, it's impossible, right? Or you might look at it up here on the very first line. The positive square root of something is going to either be positive or 0 at the very least. Now make it bigger by adding 1 to it. Is it ever going to be 0? No. So remember, the purpose of this class is to get you to think. And if you set it up like this and you just think about it, you might realize straight from here that I don't even need to do all this work because it's never going to be 0. All the values clear the denominator. All right? So x equals 3 was extraneous. So we don't need to exclude him. He is not causing a 0. So our domain then is just going to be the set of all x such that x is greater than or equal to 2. And we avoided a costly lawsuit potentially from x equals 3. It looks like I wrote greater than or equal to, greater than or equal to. One of those is greater than or equal to, and the other one is a 2. How about that? I make a 2 like that. That's a funny looking 2. I'll leave it like that. Ooh, that feels weird. That feels weird. Like brushing your teeth with your other hand. We'll just do that. X is greater than or equal to 2. Okay, cool. Y'all got the idea? Letter B then belongs to you. Very similar. You do B on your own. Use letter A as an example. Q of X is equal to that. Go. You're doing your I will of the day, by the way, in here. You are finding values that make denominators zeros and negatives under radicals. You're doing your I will in here for the day. So mission accomplished. So check the value that you get. It makes the denominator 0, and just make sure that it does, in fact, or not, make the denominator 0. All right, I'll catch up with you here. I spy a radicand under a square root. So x plus 5 is going to be greater than or equal to 0. X is greater than or equal to negative 5. I'll pick a value bigger than negative 5, like 0, to see if it works. 0 plus 5 is positive. Who cares? It's good. Now I have an entire denominator with a variable. So I set the entire denominator equal to 0. Now, before you jump in and do the algebra, think about whether it's going to give you an extraneous solution or not. If I take the positive square root of a number, it's going to be a positive number or 0 at the very least. It's going to be positive or 0. If I then make it smaller, is it possible that it could equal 0? If I take a positive number and make it smaller, could it be 0 possibly? Yes, right? If I took a positive number and made it bigger, it's not going to be 0. But I have a positive number and I'm making it smaller, there's a possibility of a 0. So I'm thinking that this one will not be extraneous. So let's go for it. We isolate the radical. We square both sides, and we get x plus 5 cannot equal 4. And there's your red flag, or in this case, your charcoal flag. We solve, and we get x can't equal negative 1. And then we quickly check. We plug that back into the denominator where I've highlighted it. Negative 1 plus 5 is positive 4. The square root of 4 is 2. And 2 minus 2 is 0. Aha! We got you, negative 1. We nabbed you. Now we're going to take your mugshot, just like Donald Trump did yesterday. Yeah, if you haven't seen his mugshot, you could Google it at your leisure. Donald Trump mugshot. The only former president ever with a mugshot. They said he only weighed 215 pounds, though, being 6'3". That's kind of a specious number. All right, we do need to combine them now, both of them. We'll say the domain of Q, or Dairy Queen, if you will, dq, d sub q, the set of all x such that x is greater than or equal to negative 5, comma x can't be 1, negative 1, sorry, or d sub q colon x epsilon. Start at negative 5 with a bracket, cruise to negative 1, step over it, and then go to infinity. There it is. All right, so you know how to do those, right? How much time we got? We got a little bit of time. Let's do one more. P of x is 4 times the square root of x squared minus 4 minus 4. It says to verify on the calculator. Maybe we'll have time to do that. This will give me an opportunity to show you that calculator. Do I have a denominator with a variable in it? You see a denominator anywhere with a variable in it? I don't either. Do you see a square root or a fourth root with a variable underneath it? Yes, it's x squared minus 4. So I come off here and I say x squared minus 4 has to be greater than or equal to 0. Now, for the first time, we have an inequality that is not linear. This is not x to the first. This is x to the second. You cannot solve a quadratic inequality algebraically. There is no do it algebraically, but remember to flip the inequality if you do this or that, like you can with the linear. There's no fix for it, okay? So all you have to do to solve this inequality is to solve it graphically. Okay, so how are we going to solve it graphically? If you think of the graph of y equals x squared minus 4, we know that that's a parabola that opens up, right? It has a y-intercept down here of negative 4, and it opens up like this. I want to know for what values of x does that thing live on or above the x-axis, right? On or above the x-axis. That's what it means to be greater than y equals 0. For what values of x is that graph on or above the x-axis? Well, if you look at the graph itself, you can see that it's above the x-axis where I highlighted it. That's going to be outside your x-intercepts. Outside the x-intercepts. This graph is negative between the x-intercepts. So if I could find the two x-intercepts, I know that the solution is going to be everything to the left of the first one. That's going to be positive. And everything to the right of the second one. So how do we find x-intercepts or roots or zeros of a function? We set it equal to what? We set it equal to 0. Yeah. Now, Once you set it equal to 0 here, you have a couple of options. You can bring the 4 across and extract the plus or minus square roots, or I'll show you here, it actually factors. X minus 2, x plus 2 equals 0. Not doesn't equal 0, we're looking for the roots now. So it's x equals plus or minus 2. So this value here is negative 2, and this value here is positive 2. And I want to know for what values of x is the graph positive. It's outside the x-intercepts. So here's what we're going to do for our solution. The domain of P then is going to be the set of all x such that x is less than or equal to negative 2, to the left of or at negative 2, or, we'll write the word or, x is greater than or equal to positive 2. This is what we call a disjoint set. Disjoint means mutually exclusive, which means there's no overlap. The value is either to the left or to the right. And you can't find a value that is in both of those intervals, right? It's one or the other. It's an or case. If you wanted to do that in interval notation, it would be x epsilon, and you would say negative infinity to negative 2 with a bracket, union bracket 2 to infinity. Yeah.
I missed why we weren't, like why it's important.
Why we what?
Why we're going to the infinities instead of towards the.
Instead of between?
Yeah.
Okay, because up here, we want to know where x squared minus 4 is what? How would we read that? Greater than or equal to 0? 0 is the x-axis. So I wrote up here, it's the same thing as asking yourself, for what values of x is the graph, or are the y values, on, that's the equal sign, or above, that's the greater than, the x-axis. So where is this parabola above the x-axis? I highlighted it. And for what values of x does that happen? Is the graph above the x-axis between the x-intercepts? No, between the x-intercepts it's below. It's outside the x-intercepts where the graph is above, okay? When we solve a quadratic inequality, the answer will always be either between the x-intercepts or outside the x-intercepts. It depends if the parabola opens up or down, and it depends if the inequality is greater than or equal to. But it's always going to be either between them or outside of them. And in this case, it's outside of them. And we don't have time to verify it on the calculator, which is fine. We don't need to verify it on the calculator because we're awesome. Okay? So now when you have these quadratic inequalities peeking up in your homework, you'll know how to solve them. You do them graphically. Find the x-intercepts, return to the inequality. You want to know where it's above. Is it between them or is it outside of them? Okay. Yeah, so be ready for a quiz over one like example 5 on Monday and keep chipping away at your homework. Any questions? All right, y'all are a good live studio audience today.